and you can see it is a usually the old say travel suitcase. Within that suitcase we have placed our system and we have measured that at Farakka. This is the real life testing we have performed, and we have got different types of readings. And as we have designed this kind of an instrument, we just patented that, and the patent was granted. And these are the results I can show you, that from the current measurement, it is in the log scale. So that is why the waveform looks like this. It is not like the exponential curve, because it is, we have placed that in the log scale. So therefore, here you can see it is picosiemens per meter. That means this is the conductivity. And red curve, that is higher the current, means that is your conductivity is high. That means the condition of the insulation is poor. So from these different types of conductivity, the different types of curves are there. So from these curves, you can generate a rule base. From that, you can have the idea of the insulation. So that is the basic idea. That means from polarization depolarization current and the conductivity, from that conductivity you can see that they are quite different, and conductivity of the insulation should be low. And if this insulation has it having higher conductivity, that means it is poor in condition. Here also the temperature variation is there, because you know whenever the transformer is running, the oil temperature is not a fixed one. So you should not test at a particular temperature, or even during temperature your temperature may vary if during your experimentation. So at different temperatures we have recorded different graphs, and all of this combination we have just made some algorithm there, because algorithm designing part is quite different. So I am not discussing that here. I will discuss something that will be easier to understand in this sort of a lecture. So therefore, from this kind of curves, we can have a program that will give us the condition of the transformer. That is the basic idea of the recent this PDC measurement. And you can see the current magnitude. It is real life recorded at on field as well as in our lab. So it is in the nanoampere range. So these are the very low current, and there are certain problem with low current, that is noise. I am just not discussing the noise part here. I am just giving you the idea of the method. And the last one for my topic, that is the detection of partial discharge. Partial discharge, you know, if there exists some void, some defect in the insulation, maybe it is not a direct short circuit. For example, say you have an insulation of say resin. So that within that resin, if some void or some air is there, so the dielectric constant of that air is less than that of the resin. So some electrical stress will be there. So if some electrical stress will be there, if some electrical stress is there, then what will happen? Local discharge will occur. And gradually that local discharge, local sparking, that will damage the insulation gradually. And right side in the, you can see the dark places, that means the gradually those portion of insulations are burnt. And after some days, after some years, after say a few months maybe, the entire insulation may get damaged. So if you can detect the partial discharge, the local discharge within a transformer earlier, then you may take the precautionary measure. So that is why measurement of or detection of partial discharge is also important for condition monitoring. But that is one classical method. That is a very classical method. That is, it is not that it is a new one. But there are new methods for to localize and to classify or better detection of this partial discharge. And this is one particular setup. I am just shown it in terms of say one sample, and by using the setup, this setup we have also designed in our laboratory, and we have just recorded the signals. For example, we applied the partial discharge measurement is done in that way. That means the voltage is being applied to the sample, and if partial discharge occurs, say your supply is 50 hertz and your partial discharge signals, they are of high frequency pulses, because discharge pulse are say not continuous. Partial discharge means the some burst of pulse, that means some intermittent burst of the pulse, like impulses, they will be generated, and some sort of a sparking sort of thing. So therefore, those high frequency signals, they will be tapped using this coupling capacitor and they will be recorded. Okay. And if we record it, you can see these are the kind of signal we have recorded, and these are the real life signal that we have recorded in our laboratory. And this, the left side, you can see, please follow the cursor, you can see there and there. These two positions, there are certain higher amplitudes, and they actually over the base noise, there are some oscillations all over, and there are certain portions with having some small higher portions up there. So higher amplitudes are there. So they actually indicates the occurrence of partial discharge. But you can have an idea of looking into the waveform that it is very difficult to identify them manually, because already there are certain noises. So therefore, these pulse, they will generate a voltage level of very small amplitude. That means that can be an amplitude of say less than say 1 volt or order of millivolt. We have to amplify them. We have normalized. I have plotted that in the normalized scale. So that is in between 1 to -1. But usually that amplitude is of the order of say millivolt in terms of voltage. Okay. Actually, discharge means some sort of charge that using some calibrator we can convert this voltage into some charge. But for the time being, forget about the charge. Let's say that we are having some signal. Our objective is to detect the location or type of the partial discharge that is occurring. And the right side one, this B, figure B, is your say 50 hertz signal, and if we apply some voltage across the 50 hertz, if we just take that partial discharge signal in terms of the 50 hertz signal is superposed on the 50 hertz signal, it will look like this. So the image that the circuit diagram that we have shown here, and the instrument, that detector, we have designed that, I told you, and that we have just patented there, and we have also the patent is granted. But the main objective now is we have got the data. So how to measure the data, we have discussed that part. Now what to do with that data, that means how to understand the condition of the transformer, that is the main part. So first of all, I told you that the condition monitoring problem can be say divided into two parts. The first part is data acquisition, and the second part is the analysis. And the analysis can also be just classified into two categories. That means once you have the data, let us extract some suitable feature. Feature means some signatures, some indicative signal, indicative say attribute that we can take, and then we can design some algorithm so that we can have the idea of the condition of the system. So again, the analysis part can also be divided into two categories, and it is not only true for this transformer condition monitoring. In many applications where you are say applying some knowledge of some say fault classification or something, the overall system can be classified into this kind of a functional parts. So therefore, this approach can be applicable for many other problems also. That means you can have the feature extraction and then you can classify them. So, but provided the data is noise free or properly denoised. So first of all, we are discussing the impulse waveform analysis that I have shown you at first. That is this one. That means we have to apply some impulse voltage, then we have to record some response, and usually there are some standard rules. That means which voltage you have to apply on which rated transformer. There are certain rules, and those rules are given in IC, that is a standard, international standard, that IC 60076 part 4 is used for that. And if we just apply some voltage, today I will be showing two models. One is some digital model and another is some analog model data, and this is the diagram, that photograph of this, and the right side is the schematic of that. So that means if you look into this, you can see different, say this kind of copper colored thing you can see, and if you look closely to that, you can see that there are some discs. That means they are one coil in a shape of a disc. So these are the coils, and in this particular transformer there are several of such things, and we created certain faults. That means, say if the insulation of, say, disc number, say 30 is weak, that means we have shorted the disc. Now our objective is to identify the position of the fault. That means at which position the winding is weak or faulty. So this is the scheme. That means we have discussed with two kinds of a fault of the winding. One we call series fault. Series fault means that particular disc that will be shorted. That means the winding, you know that whenever we make one winding, that means the wire should be insulated from each other. So otherwise your winding should be shorted. So if the insulation between two turns, they are removed, then the metal portions will be touching each other. So therefore we say that the windings are shorted. So that is why if one disc is shorted, that means in the model you have to short circuit them. So this is one, we call it series fault. And the other thing is that if the winding is directly connected to the ground or the body or the tank, then the winding is, we call it a shunt fault. So we have created all of this kind of fault in our model, and we recorded the data. Look into the data. This is a real life data that we have recorded using a digital storage oscilloscope. You can see this is one data, the blue one. It is, say, B. B is the disk number 80 series fault. That means there are different disks. Say this is, say, location, one particular location. Location is disk number 80. The fault is there. Then your waveform looks like the blue curve. If the same series fault occurs at 50, then your waveform looks like this. So by manual observation, it is not possible for anyone to say which curve belongs to which kind of a fault. That is why we require advanced techniques, and we have to use some computer programs. We have to apply some signal processing tools to identify that, which is not otherwise possible by manual observation. Again, for the shunt fault, again the red and the black curve you can see the same at 50 and 80 disk number. The shunt fault, the waveforms are quite different, but it is very difficult to distinguish these two. That means if our fault occurs at 51, 52, 55 or say 70, it is difficult to identify. So that is why we have to apply some signal processing tool as well as some say some machine learning algorithm for that, so that your program can do the job for you. So now if we look into the fault identification, then again I told you that can be classified into two categories. One is called feature extraction and second is called the classification. Usually for this particular lecture, I have chosen the cross wavelet transform, but whatever may be the tool for feature extraction means, I told you that it is the extracting fruitful feature from a signal. That means from naked eye, from manual observation, that may not be revealing many important information, but by feature extraction means we have to apply some signal processing tool, then we have to extract certain information from that. So that is why it is called the feature extraction, and here we are using cross wavelet transform, and whatever may be the tool, it can be wavelet transform, it can be the problem statement is important. That means then only we can have the right way of finding the solution. Most of you probably know, but if you do not know, then actually I am just explaining it. Those who do not know that. That means for Fourier transform, you know that the frequency content of a signal. That means what are the frequencies present in the signal. Using Waveform transform, we can have time frequency representation. That means at which time, which frequency is present. Transform means it is a advanced version of the wavelet transform, and cross wavelet transform means that means it correlates the time frequency domain between two signals. That means, okay. Is that audible?
Yes, sir, it's audible.
Okay. No, I have just heard two sounds. I thought maybe I am disconnected. Okay,
Yes,
it is
sir.
not.
For a brief, there was a slight disturbance, but now it has got stable. It has become stable.
Okay, okay. That's why I just stopped. Okay, okay. If any problem occurs because of the connection, if the voice fades or some problem occurs, please just inform me. Okay,
Yes,
because during presentation I cannot
yes,
see
sir.
the
Yes,
other
sir.
window.
Yes, sir.
So either call me, or if I am disconnected, either call me or send me a message. Okay,
Yes,
in the
sir.
mobile.
So, can you just return to that slide cross wavelet transfer which
Yes,
you are
yes,
explaining? Why?
yes,
So, from that portion, what I observed, there was slight disturbance. So,
yes, yes, yes. I'm just explaining that. So the cross-wavelet transform actually gives us the idea, or it compares two signals in the time frequency space. That means, say the cross-wavelet coefficient is higher, means at that time and frequency region, the two signals, they are having some common feature. Let me explain. See, these are the two signals. Okay. If we perform the cross-wavelet transform as per the equation shown, it will give you this kind of a plot. And this kind of a plot, if we magnify it, it looks like this. So if this is the plot, the red region means higher value. That means at this region means for this curve, the x-axis is the time axis and the y-axis is the scale. Scale is basically inverse of frequency. So for the time being, we can say it is a frequency axis. So x-axis is the time axis, y-axis is the frequency axis, and between two signals where this particular value is high, that means say the red region, say near 100 and 256, it is say red. That means 256 means say for example it is say corresponds to 1 kilohertz. So 1 kilohertz signal at 100 microsecond, between two signals they are common. And blue means at these regions, these two signals, they are having less common features. So that means the higher portions will give you the common frequency features in the time, at a particular time. So what is the basic objective or basic understanding of cross-wavelet spectra? The cross-wavelet spectra gives the comparison between two signals in time frequency domain. That means at which time, which frequency component, they are common between two signals. Actually, they are plotting this. And you know that from the Fourier transform knowledge, the coefficient can be complex. And if that is a complex one, you have a magnitude as well as phase. The same thing occurs for this wavelet coefficient and for the cross wavelet coefficient. And arrow means that phase. So if the amplitude magnitude is that coefficient magnitude is the color, and these arrowheads, they indicate the angles. That means the right side arrow means 0 degree, say vertically up means 90 degree, and so on. In this way, these arrows indicates the phase. So now from this waveform, if we just take this kind of a statistical features, these are the statistical features, and we name them as F1 to F12. It is not, there is no guarantee that in all the problems only these features will do. Now that is the understanding, that is the experience of the user or the programmer, not the programmer, I mean that system engineer or the researcher. He can understand that what should be the features we should take. So that is why either you can look into the earlier published papers, or you have to do some trial and error method to look into which features are good for your problem. So here we have just performed some statistical features. They are a sort of a moment, statistical moment, but of a different kind. So we have taken this kind of a feature, and if we just plot them, or if we just try to fit them in a classifier, we will get the information. So the cross wavelet, why we have chosen the cross wavelet? Because whenever we cross correlate, it is sort of a cross correlation, and you know that if some random noise is there, to the cross correlation of two random signal, they are of very low correlation coefficients. So that means if there exists certain noise in two signals, some random noise, they are uncorrelated. If we perform the cross wavelet transform, the effect of noise will be minimized. So we do not require a separate denoising scheme. So cross wavelet transform can act as a tool to reduce some amount of random noise. So that is a helpful tool. So that is why we used cross wavelet transform. So that is the logic. And classification, again, now I'll just explain the rough set theory here a bit. And again, the same question. There are hundreds, 10,000s, and many more classifiers. Those who are involved in research, they can understand that there are so many classifiers. Every day in some computer system journal, they publish a new classifier, new machine learning tool. So why we are, or which tool we should choose? So again, the same thing, the why should be very clear. And again, the problem statement plays a key role here. If you have the clear idea regarding the problem statement, you can have the clear answer for that. And that will help you in the choice of your classifier. So we have chosen the rough set theory. Why rough set theory? Because I told you that this kind of a feature, you do not know whether all these features, say I have taken 12 features. Now, how many features is sufficient? Or whether this F1 and F2 and F3, they are all the same. They are meaning all the, I mean, for the particular problem, whether they are giving more or less same trend. We do not know earlier. So, it may so happen that even though you are taking 12 features, maybe they are not sufficient, or it also can happen that many of the features, they are giving you same information. So rather than using 12 features, you could have reduced to say 5 to 10 features. So you can reduce the features. So whenever we are extracting a feature, there is no way we can understand that which feature is going to be fruitful for our problem. We have to do some analysis for that. And one way of doing this is the use of the rough set based classifier. Why? Because rough set based classifier can remove the superfluous information. Superfluous means some extra information. Say if F1 and F2 feature, if they are same, they are almost giving you same information. One feature can be dropped, one feature can be removed using rough set. And also there we do not require any a priori knowledge, because in many cases really we do not have the knowledge. That means if you are targeting one new problem, then how do you know that which feature will be fruitful for you? So for rough set theory, a priori knowledge regarding suitable features is not required. Whatever the possible, all possible features you can take, then you can eliminate them one by one. So that is why we have used here the rough set, because we have used the cross wavelet transform for the first time, and we had no idea that which features will be very good. That's why we have chosen the rough set theory, so that we can eliminate the superfluous information, and as well as we can keep the important features. And there are some mathematical tools. I am just explaining them, like an overview, because rough set theory, if I am going to explain, that requires a total entire semester maybe. So first of all, step one, the data table should be discretized. Discretized means, say it is a sample table. Say you can see object means different cases. Say for 1 to 89 means these are the different fault cases. And fault decisions or the fault names, these are the classes, the green color, AC1, the decision attribute, AC1, SC1, SH1, SH1. That means here SC1, SC1 means we have taken two data for the same fault here. Because while you are taking the data, you should have some training and testing. So therefore, we have taken the data for the same type of a fault, not only once, but for more than one time. Okay, so that is why the data table that we have got is that will look like this. That means different cases, and the condition attributes are nothing but the features. So F1, F2, F3 up to F12, they are the features, and these are the decision attribute. So I have normalized the values. So between 0 to 1 we have plotted. So 0.95, 0.43 for different cases. Feature F1 having different value. Feature F2 is having different values. F3, F4 and so on up to F12. If a computer program is given input this table, so how it will understand that for a particular input, for a particular case, or for a particular set of features, what is the fault? That is the problem statement. That means if you are given this table and if you are given an unknown case, you have to identify the fault case. That means these are the known cases, some of these known cases, and if the unknown case comes, then you have to identify the fault. That means whenever the unknown case comes, unknown case will give you, say, one particular values for each of the features. And that particular values, one setup, say for example, one row is called a feature vector. These are some technical terms usually we use. Most of you probably know all these things, but I am specifically saying this for the students. So here, say this is one particular row. If we look into, then it will call one feature vector. So one particular feature vector, if it is given to the program, it should be able to tell you that which fault class it belongs to. So that is the problem. So that is the problem statement. We have to do that using the rough set theory. So the first step is we have to discretize. So here you can see 0.95, 0.43, 0.90. So you have to discretize means we have to segregate them in terms of some discrete ranges. For example, say from 1 to 0.9, whatever may be the value, we call it say 6, just like that. So how to determine that? There are some algorithms. I am just avoiding that. There are some, but I am explaining the steps only. So from the earlier table, this one, we have to get this table. Now, not much of variation in the data value, because all of those different values, they are mapped with some, say, discrete number of values. For example, from 0 to 6, only 7 values. All the values can be mapped within these 7 values. here for the F2, for F3, and so on. Now the second step is identical attributes and cases are eliminated. There are different mathematical steps, and we have found out, because I cannot show you because the entire table will be very large, only a computer program can handle. Manual checking is not possible. So from the computer program we have checked using some method as described in the rough set theory. We have found out that F4, F6, F9 and F10. Initially we started with 12, but we have seen that these 4 features can be eliminated because they are almost giving you the same information as those of the others. So there is no point of using extra memory storing them. So we can remove them. So that is one particular aspect of rough set theory, that it can eliminate the superfluous data or the extra information. And redux or core are obtained. Redux and cores means which are the important values. Say it can be F1, F3, F5, all other features, but which are the important values have the most effect on deciding this class. So if we just get into this step, we can see now our table, information table or the data table that we have got has become little bit simpler. For example, say for fault number 1. So fault number 1, say feature 2, feature 7 and feature 11. Those values, they can be only looked into. Other values are not very important to identify this. So in this way, we can identify the fault locations or the fault types. So now we can have the if then else rule, because how, say here, like just take the first one. F2 is 5, F7 is 2, F11 is 1. So let us write down. Say F2 is 5, F7 is 1, F11 is 1. So if F2 is 5, F7, this A means it is the logical AND. So F2 is 5 and F7 is 1 and F11 is 1. Then the location and type of fault is AC1. That is series type fault at location 1. Just like that. So in this way, we can have several such rules, so that if the rule is there, then if the data comes, then you can perform your operation, cross wavelet, etc. You can discretize and you can find out, you can check which rule it is firing or which rule it actually allowing to be true. So that is why which rule is the rule it actually fires or makes true will be the case of the fault or the location of the fault. This is the basic idea of analyzing the fault data using rough set theory. So now we have just some data. The accuracy was quite good. If we increase the data or some better feature if we can take, then accuracy may be increased. The same thing I told you for the partial discharge. Now we can speed up a bit. So I have just performed this in this way. That means this is the noisy PD pulses. The partial discharge signal we have recorded is the part PD pulses. This is the power frequency signal. This is the plain sine wave, the 50 Hz signal. Then we have add them up. This is the signal we have got plus this signal plus this one. We have got this, and we have performed the cross wavelet between these two, this one and that one. And the waveform looks like this. Let us have a bigger magnified view. Is this one. Usually the PD pulses occurs, I told you that these are the regions where the PD pulses occur. That means in a full cycle, the right side diagram is the full cycle. In the full cycle, in each half cycle, there are regions where the PD pulses occurs and change in colors. And that is why the success of the application of the tool, the cross wavelet we have performed, and it gives us the correct indication. And you can see in these regions, the color changes. That means the correlation is established. So that is why from this diagram, we can identify that at which locations the PD pulses are occurring or what is the nature of the PD pulses. See, from this diagram, from this waveform, it is not very clear. But if we plot this one, the cross wavelet spectrum, it is very clear that at which regions the PD pulses are present. So that is called the feature extraction. That means we have to use certain tool which makes you understand it better rather than your recorded raw data. Raw data may be not that much clear to you, but if we apply the proper tool, then the other hidden aspect of the information in the signal that can be viewed. That is the purpose of the choice of right tool for the feature extraction. And again, we have just performed some statistical parameters, and these are the parameters. We have just chosen only here 7 features. 7 features we have plotted with respect to A1. Say 6 plots will be there. 7 features. A1 with respect to A1 we have plotted, and these different colors mean different types of PD, and they can be identified from these plots. We can see that they can be identified using some rule base because they are at different positions. What are the different colors means? D1, D2, D3, D4. You can see here there are 4 colors. 4 colors: D1, D2, D3, D4. And what are the D1, D2, D3 and D4? They are basically, D1 means narrow void contact to the electrode, D2 is narrow void away from the electrode, D3 is large void or large void in contact with the electrode, and D4 is a large void away from the electrode. For simplicity, I have taken only these 4 classes. It can be made much more complicated. There can be several this kind of cases are there, and your system will become much more complex. But I am just showing these 4 cases to understand the whole thing, because if we just take too many of classes, then it is difficult to understand. So again, the same 5 steps of the rough set theory, and this kind of a table we can find out, and we can have this kind of a rule base we can again generate, and we can have this one. And here I have just particularly shown, even with the noisy data and denoised, you can see the performance is more or less same. That means the cross wavelet transform has that particular effect of removing the effect of noise. So that is why the choice of the tools, that should not be abrupt, that should not be anything off the shelf you can pick anyone randomly. It is not that. So with the purpose, what should be the particular objective, what is the specific problem statement, what is the requirement of the system, depending upon that you have to decide on both the things. One is the feature extractor, and the number 2 is your classifier or your analysis tool. So there are different types of methods nowadays of computing techniques, as I have shown you that these things are you can use, and also you can use denoising, feature selection, some minimal feature selection. That means we have to minimize the feature, we have to classify, and also you can design an expert system so that the data acquisition and particular analysis will be performed by the expert system, and it will give you the result. So this is the overall scheme of condition monitoring nowadays in the recent era. And whenever you get the opportunity for giving some lectures, it is mandatory to blow your own trumpet. So I am blowing my own. So this is the book we have just written under the guidance of my teachers, and say during my research work, that is long ago, but still we call it a recent trends because some advancements are there, but the basic classical and some knowledges regarding the even for the recent trends have not been changed yet. So that is why this is the book we have published on this. And this work is a large one. You can understand looking into the volume of the work, so that requires a very good team. And I am thankful to be a part of a very good team with very stalwarts. My colleagues are also there, senior colleagues, and my senior researchers in our lab, and my guide says, okay, because to get the data and other things to have, because it is not possible for only one person to do all the things. So that is a good thing for the teamwork. And thank you. If you
Thank you,
have
sir.
any question, you can
Thank you,
ask.
sir, for your very excellent and detailed lecture. The lecture content was very nice to listen to, and we have we have learned lot of things. Especially what we learned is that being electrical engineers, we have to gradually, or rather, in a urgent way, learn the skills which are related to machine learning and artificial intelligence, some statistical techniques, including the signal processing, what you have explained in your lecture, that being electrical engineering,
Okay,
it,
I'm probably 5 minutes late.
it's
Okay.
not an issue at all, sir.
Okay.
We have that kind of leverage with us.
Okay.
It's
Okay.
not like
Okay.
that, sir. But the important thing is that the lecture was explained very uh, vividly and lucidly. I mean to say, even if somebody is not aware of these things, so just by listening, that person will have definitely learned a lot of things. This is my
Thank you. Thank you.
personal
My objective was to just to give that if somebody becomes interested, he or she can pursue in this
Yes,
particular domain of.
definitely, sir. You have shown us a lot of areas in which people can take up research work, especially the condition monitoring, and it is very good for all the participants to get exposed to this area of research. So, thank you, sir. And I would now hand over the session to Mr. Afaq Wajid. Over to you, Afaq.
Thank you, sir. Thank you, Dr. Devanshu Dev, for to invite questions from the audience for sir. If you have any questions, you may please ask, sir.
Sir, can I have one question?
Yes, please.
Yes, sir. Actually, sir, you have discussed in a very elaborate way the condition monitoring, and the area you focused was the insulation which is used in the transformer, be it the
Mhm.
oil or the insulator. I'm correct or not, but the core of the transformer, so that also gets some sort of aging, and the deterioration
Yes,
of the core as
yes,
a
yes.
magnetic material, that also may be having some effect on the operating performance.
Yes, yes,
So are there any statistical or signal processing technique which is especially non-invasive? As we have pointed in the beginning, that there is a invasive and non-invasive.
yes,
So
yes,
you have discussed mainly the non-invasive techniques where we don't
yes.
need to take out the oil or the insulator like that. So
Mhm.
for testing the health of the transformer core, so that there is no sort of magnetic unbalance or some magnetizing current unbalance or those things takes place. Are there any techniques? I just I don't know, but I just wanted to know.
Now, there are my discussion was related just related to the insulation, mainly insulation and insulation. So one way of doing the insulation is the local defect and the overall. I have mentioned that is the overall effect of the overall condition of the insulation, not any condition at any point. But for the partial discharge and impulse fault, that is the local understanding if there is any local defect or not. Similarly, for the magnetic circuit, there are certain
Hello.
line. Hello.
Yes, sir.
Myself, Professor Jana speaking. Sir, I do have a question. In continuation with Professor Deepak Shaw,
Uh-huh.
Sir was asking basically, let us put it this
Yes,
way.
yes.
Initially, the, let us say, BH curve,
Uh-huh.
while let us say it is a new transformer, so the operating point on the BH curve may be in some location. Okay. So after aging, let us say after 4 years or 5 years of service, if that gets deviated, so definitely if the operating point of BH curve gets deviated, so definitely it will have an impact on the performance of the transformer. Do you have any idea, or can we really think of
Yes,
that
definitely it will.
any
Yes,
kind of
that is
aging
a very
of the
good
core
question.
material, definitely we will have shifting of
Yes.
that operating point. And as you know, if the operating
Mm,
point gets shifted, so definitely your
mm,
that
mm,
E by V, that is let us say E by N
mm,
rather, I should say voltage per turn also will get changed. and if E by
Yes.
N gets changed, so the overall everything will get
Yes.
changed, isn't it? So is
Yes.
there any
Yes.
kind of
That there
work?
can be
Yes, sir. Please, sir.
that
Please.
that can be there. Yes, that can be there. But the point is that that particular effect, because you know that voltage and other things have some tolerances. If even if you have some deviation, the loss and other parameters, they will vary, but it will not entirely make the transformer out of service. So that is why importance is much more. That means before of degradation of that level for the core, the insulation may get damaged. So that is why first importance usually given to the insulation condition, not to
Okay.
the core,
That
but
point is
but from the
well taken, sir. What I'm
yes,
saying,
yes,
that point is
that is,
definitely as far as
yes,
health.
I'm
Yes, as
yes,
far as
but
health
there
of the
are
transport. Huh.
there are other ways of doing studying the magnetic circuit, but
Yes.
as I am not
Okay.
say doing research on or working on that, so I am just not I have just skipped those portions.
No,
But
no, this.
still, but there are other methods. There are methods where the magnetic asymmetry and the performance. But I am unaware of that whether that they can be done online or in the non-invasive way.
Hmm.
Probably that non-invasive, that is possible because you have to have some say loss test there. But precision loss testing for the modern day transformers, that I am not aware of, because I do not gather information regarding that, as I do not work on that. But
Hmm.
still I have just some of my colleagues, they actually work in Germany on the on this aspect. That means what is the asymmetry or the problem, say initial condition of the magnetic circuit, and with
Yes.
aging what is
Yes.
the how much it deviates in
Yes.
terms
Yes.
of the
Yes.
magnetic circuit
Yes.
of the transformer.
Because
There are
because
other,
because
yes,
because the operating point will have the effect on the, let us say, losses also,
yes,
isn't it?
yes, that,
If
yes,
the
that,
losses gets changed, so
yes.
definitely your efficiency also
They
will get
actually,
changed.
yes,
You will
they
be.
actually study
Yes.
that.
Yes. Yes. Yes.
Yes.
Oh, thank you. Thank you, sir.
Thank you, sir. Thank you,
Mhm.
sir.
So now I would like to begin with the valedictory session of the day. We have our group director, sir, with us. I would request sir to say a few words.
Very good afternoon, one and all presents in this webinar. Firstly, on behalf of our Honorable Chairman, Mr. Jagannath Gupta, our Vice Chairman, Mr. K.K. Gupta, our Executive Director, Dr. Shubhangi Gupta, and our CEO, Sir, Dr. Balaram Gupta, I would like to convey my heartfelt thanks to all the dignitaries, those who have enumerately took the session with the highest level possible. I personally like to congratulate Professor Dr. Debashis Chatterjee from Jadavpur University for yesterday's session, as well as Professor Dr. Jitendranath Bera. They have conducted a fantastic session in both the hubs. It was really encouraging for the teachers, faculty, and the procedures, students. And in today's session, we found Professor Dr. Shobhan Dalai and Professor Dr. Devanshu De. Both are from Jadavpur University. The condition monitoring was the topic for the day in other form. This webinar really, I would again like to thank the Department of Electrical Engineering of Bajbaj Institute of Technology to think about this topic, to choose the topic. It is again very relevant uh, for the society, and I feel electrical engineering department have lot to contribute in the modern development in the era of Industry 4.5, where IoT, AI, machine learning, all these things are uh, blend together with every scope of engineering goods. So that way, the session, as I wished yesterday, the full successful. Now I declared it is a successful webinar, and I'd like to congratulate the Department of Electrical Engineering and convey my best regards to the dignitaries, those who have taken their session, neglecting their usual time. They have sacrificed their time for us. Sir, I am very happy to see you all here, and you have enriched us, and I am really thankful to all of you. I hope that in future, mm, again, we will seek your contribution. All of you will be with us in future, and it is a win-win situation. We are passing through a very serious pandemic period. We do not know when will we come out of this situation. It will take time, maybe years, though slowly we are opening the sectors of life operations. But yes, academics is not in that way got the priority or the scope, whatever it may be. But academicians and academia struggling hard, showing the path to other sector of the society, what best they can do with this threat. So I congratulate my colleagues, my Dean Academics, Dean Diploma, Dean MBA, HOD Electrical, and the coordinator of the program of from Electrical Department. And it's really amazing program you have concluded. And now I declared the program is really a successful one, and keep it up for the future events also. Thank you one and all, those who have attended for the webinar.
Thank you, sir. Thank you for
Thank
your
you.
inspirational words. Now, I would like to request our Dean Academics, Professor Dr. N. Jana, to say a few words.
Very good afternoon, everyone. I think Professor, our group director, sir, has almost covered everything as far as the outcome of this particular webinar is concerned. He has very largely took the spectrum of really what are the objectives of the things and what would be the outcome. But I would be, as a head of the electrical engineering as well, I would consider as a success one only when some of our students or even faculty really can take up some kind of research work out of this webinar, then only, yes, it would be called successful. But definitely there should be some beginning. So in the beginning of the new year, we have also began our this session. So definitely the organizing team with our two conveners and joint convener, they took up the challenge to really have this kind of seminar in the beginning of the year, and definitely we are really elated. So as far as our delegators are concerned, they have spent their time with us, and we will be with you, sir, to take up some different session in different time dimension. So thank you, all of you. And I would say that definitely it would bring some outcome out of this particular 2 day session. Thank you. Thank you all.
Thank you, sir. Now, we have our Dean Diploma, Professor Dr. Shiladitya Bandopadhyay, sir, with us. So, I would request you to please say a few words.
At the outset, I would say, in fact, to conclude, I would say it had been a very good session for 2 days, and I think we all have been educated by our esteemed guest speakers, and it had been really fantastically educating session for our students also. And I would like to congratulate our Department of Electrical Engineering for arranging this webinar, as well as I would, on behalf of BBIT, I would convey my heartfelt thanks to our esteemed speakers. Thank you very much for inviting me in this great session. Thank you.
Thank you, sir. Now, with this, we have come to the end of this webinar. I take great pleasure in informing you that we had over 500 plus viewers in the past 2 days watching live on YouTube, apart from the industry professionals, faculty members, PhD scholars, and other delegates watching us on Google Meet. So, thank you all for joining with us and making this webinar a grand success. And in this situation, in this pandemic situation, one simple message for all of us: stay healthy, stay safe. And once again, I would like to thank Dr. Devanshu Dey, who is present with us, the other three speakers who were there present with us for the like previous three sessions. They could not make it due to their online classes. So they have also extended their heartfelt thanks and gratitude to us. So let us end this session with a heavy heart that we'll meet once again another time, another day with a different topic. Thank you all.
Thank you. Thank you.
Thank you, sir.
Thank you. Thank you.
Thank you, sir. Thank you.
Thank you all.
Thank
Thank
you all.
you. So I'm leaving.
Yes, sir. Thank you all of you, sir.
Yeah,
Thank
thank
you all
you.
of you.